How a single molecule decides whether food spoils or survives. It sits quietly unseen, deciding the fate of every meal you eat. One molecule determines whether food nourishes you or turns dangerous, and it makes that decision faster than you realize. To understand why food spoils, we have to look beyond time. Spoilage is not about age alone. It is about chemistry gaining momentum. From the moment food is exposed to air, reactions begin. Molecules interact, exchange energy, and seek stability. What we call freshness is simply a temporary balance. Modern supply chains stretch food across continents. Storage delays replace immediacy. Packaging becomes a chemical shield. Yet the same molecular rules still apply. One molecule often stands at the center of this process: oxygen. Invisible, reactive, and relentless. At first, oxygen seems harmless. It keeps us alive. It preserves color and texture briefly. But oxygen also accelerates decay. It strips electrons from fats and proteins. This process is slow, then sudden. Food chemistry begins to unravel quietly. The initial electron transfers that oxygen initiates are small. Each individual reaction alters only a fraction of the food's molecular inventory. The first narrative beat starts with exposure. A package opens. Air enters. Oxygen molecules collide with food surfaces. Reactions initiate without warning. The second beat follows quickly. Microorganisms exploit these reactions. They multiply, feeding on chemical instability. Spoilage is no longer passive. It becomes active. Then comes a third beat. Protective molecules attempt to slow the process. Antioxidants donate electrons to stabilize reactions. Packaging limits oxygen flow. Temperature reduces molecular motion. For a while, the balance holds. The antioxidants in food, vitamins, polyphenol, flavonoids, are not passive bystanders. But beneath the surface, chemistry keeps counting time. Because one molecule does not stop reacting. It only waits for opportunity. And that is where the story begins to sharpen. Oxygen never works alone. Once it starts reacting, it creates momentum. One reaction opens a door for another. Electrons shift. At first, the changes are microscopic. Fats begin to oxidize at the surface. Proteins lose their original structure. Flavors flatten, then turn sharp. You cannot taste it yet. But chemistry has already moved forward. This is where the story deepens. Because oxygen-triggered reactions create byproducts. These byproducts accelerate further decay. It becomes a chain reaction. Each step makes the next one easier. What began as exposure becomes transformation. The chain reaction nature of lipid oxidation is particularly consequential. Free radicals generated by initial oxygen reactions attack intact fat molecules, producing more free radicals, which attack more fat molecules. Microorganisms sense this shift immediately. Bacteria and molds thrive where chemistry loosens control. They feed on broken molecules. They release enzymes that speed breakdown. The food is no longer defending itself. Its internal chemistry is losing cohesion. The enzymes that microorganisms secrete into food are not discriminating. They attack whatever structural molecules are accessible. Proteins are hydrolyzed into amino acids. Fats are cleaved into fatty acids. However, humans learn to interfere. Salt draws water away from microbes. Acids slow enzymatic reactions. Heat denatures proteins and resets structures. Cold reduces molecular motion. Each method attacks the same problem, slowing oxygen's advantage. The effectiveness of each method depends on the specific chemistry of the food and the specific organisms present. No preservation method is universal. But here is the early conflict. Every intervention changes food chemistry in other ways. Preservation extends life, but alters texture and flavor. Freshness becomes a compromise. Shelf life replaces immediacy. The molecule still waits. The trade-offs of preservation are not incidental costs. They are direct consequences of the same chemistry that preservation exploits. Salt that inhibits microbial growth also draws moisture from food tissue, changing texture. Acid that slows enzymatic activity also affects flavor perception. Packaging evolves to fight time. Vacuum seals remove oxygen. Modified atmospheres replace it with inert gases. Antioxidants patrol reaction sites. For a moment, chemistry pauses. Not stopped, paused. Modified atmosphere packaging, replacing the air around food with nitrogen or carbon dioxide, is one of the most effective tools available. By eliminating or reducing the oxygen concentration, it slows the initiation of oxidative reactions. Yet oxygen always finds edges. A microscopic leak, a temperature shift, a damaged seal. The reaction resumes instantly. No warning, no gradual return. The recovery of oxygen into a previously protected environment does not restore the chemistry to its original state. It adds a new oxidative load to food that has already been partly processed. The reaction does not start again from the beginning. This is where tension builds. Because spoilage is not linear, it accelerates suddenly. Food appears fine, then fails quickly. The molecule does not negotiate. It follows physics. The nonlinearity is spoilage. The sudden acceleration after a period of apparent stability is a consequence of the autocatalytic nature of oxidative chain reactions. Below a certain threshold of reactive species, the protective mechanisms in food can keep pace. What nobody expects is how sensitive the balance is. A few degrees, a few hours, a single puncture, that is enough to decide survival or decay. And that decision is already underway. The temperature sensitivity of reaction rates is captured by the Arrhenius equation. For many biological reactions, a 10-degree increase roughly doubles the reaction rate. This is where the conflict fully reveals itself. Because the battle over food is not between humans and microbes. It is between speed and control. Chemistry moves fast. Preservation slows it down. Inside food, oxidation spreads unevenly. One pocket reacts faster than another. One surface weakens before the rest. This creates chemical hotspots, areas where reactions accelerate beyond control. From the outside, nothing looks wrong. Inside, structure is already collapsing. As oxidation continues, fats break apart. They release compounds with sharp, bitter odors. Proteins lose shape and functionality. Enzymes begin digesting the food itself. Texture softens and liquefies. What once held together now falls apart. The reaction has crossed a threshold. Here is the critical buildup. Once enough bonds are broken, reversal becomes impossible. Cooling no longer helps. Packaging no longer protects. Antioxidants are overwhelmed. The system has tipped. Microbial growth now explodes. Bacteria double rapidly in unstable environments. They release waste products. These chemicals further damage structure and flavor. Spoilage feeds on itself. The process accelerates faster than detection. This is why food safety feels unpredictable. Two identical meals age differently. One survives. One fails. The difference is often a few molecules, a brief temperature change, a delayed seal, a moment of exposure. The sensitivity of the outcome to small variations in initial conditions is a signature of chemical systems operating near a tipping point. The paradox is unsettling. We live in an era of advanced preservation, yet food waste continues to rise because control requires constant precision. Chemistry punishes small errors brutally. It does not average mistakes. It multiplies them. At this stage, the molecule has won. Oxygen has reshaped the system, not through force, through persistence. It followed opportunity. It obeyed energy rules. The food did not suddenly spoil. It was gradually redefined, step by step, reaction by reaction, until survival was no longer possible. This buildup leads to the final truth, one that explains why this process feels inevitable, and why understanding it changes how we treat food forever. The climax arrives quietly, not as a sudden failure. The key insight is simple. Food does not spoil because time passes. It spoils because chemistry keeps moving. Oxygen never attacks all at once. It waits, reacts, multiplies, and accelerates. This changes how we see preservation. Freshness is not a state. It is an active process, one that demands constant balance. Remove oxygen and reaction slow. Lower temperature and motion weakens. interrupt microbes, and decay pauses. But nothing truly stops the chemistry. This is why modern food systems feel fragile. They rely on precision across thousands of steps: harvest, transport, storage, packaging. Every step is a chance for imbalance. Every delay is an invitation for reaction. The molecule never sleeps. The resolution is not fear, it is understanding. When you see spoilage as chemistry, patterns emerge. Why airtight containers matter. Why refrigeration works. Why small mistakes create large losses. This insight reaches beyond the kitchen. The same rule governs materials, medicine, and energy. Stability is temporary. Control requires effort. And chemistry always favors motion over stillness. Food teaches this lesson gently, with scent, with texture, with taste. It reminds us that molecules obey physics, not intention. And once reactions begin, they follow through completely. Understanding this does not make food immortal, but it makes us better stewards of chemistry, more aware of timing, more respectful of balance, more capable of working with invisible forces. Sometimes the smallest shift in perspective becomes the beginning of a new future. How a